In this video, we apply the second translation theorem, which we talked about in the last video. Remember what the second translation theorem said? It said if f of t has a Laplace transform f of s, then the Laplace transform of f of t minus a times h of t minus a is e to the negative as times the Laplace transform of f of t. Or in other words, it's e to the negative as times f of s. And of course, if this is the Laplace transform, the inverse transform just goes from right to left. So the inverse transform of this guy is actually equal to the inverse transform of f of s, that's f of t, with the t replaced by t minus a, times the Heaviside function at t minus a. And I think you can see why it's called the second translation theorem. We already had a translation theorem which moved that function f of s, a units, along the s axis. This is moving the function f of t, a units along the t-axis first, and then multiplying it by this Heaviside function at t minus a just zeroes it out before t equals a, and then after t equals a, that function f of t appears as it would have appeared had it started at t equals 0. So in this video, we're going to apply this to a couple of examples. First, we're going to compute a couple of Laplace transforms, and we will also discuss an alternate form of the second translation theorem. And then after we do that, we will compute an example or two of how we can compute inverse transforms using the second translation theorem. So here is our first example. Notice you've got a function times the Heaviside function. Just through pattern matching, if I want to use this theorem to evaluate this, I identify this as f of t minus a, and identify this as h of t minus a. And then again, just through pattern matching, if this is h of t minus a and I've got a 3 here, that means the a must be 3. So that means that this must be f of t minus 3. Now, according to the second translation theorem, we're going to get e to the negative as. And if a is 3, actually, I'll just write it over here. I know that's the problem statement, but that's okay. We're computing this, and now we're just sort of looking at this expression here. This is equal to e to the negative as with a equals 3, so that's e to the negative 3s times the Laplace transform of f of t. But that requires that I find f of t given that I know f of t minus 3. So I've got this. F of t minus 3 is 3 minus t raised to the 5th. Now, on the surface, it looks like, well, there's not a t minus 3 over here. If the input is t minus 3 and the output is 3 minus t raised to the 5th, well, we're going to have to manipulate this a little bit so that it has t minus 3's in it rather than 3 minus t's in it. I wish I hadn't picked 3 and t because they rhyme and it's making this a tongue twister for me. But basically, I need to write this in such a way that this expression right here, this t minus 3, appears on the right-hand side. Well, that can be easily done if we factor out a negative 1 here. This is negative 1 times t minus 3 raised to the 5th. And if you don't believe me, just distribute. Negative 1 times t is negative t. Negative 1 times negative 3 is positive 3. So this is really the same as 3 minus t to the 5th. And then you can think of this as a product. You've got this negative 1 times this expression raised to the 5th. Negative 1 to the 5th is just negative 1, and then we'd have t minus 3 to the 5th. So this function f of t is taking the input t minus 3, and the output is t minus 3 raised to the 5th multiplied by negative 1. So in general, for something in the domain, this is saying we're going to take the input and we're going to raise it to the 5th power, and then we're going to multiply by a negative 1. Well, rather than putting this little star here as a symbol for the input, star is not in the domain, obviously, it's not a number. We're going to put a t there for our input. So if f of t minus 3 is negative t minus 3, or negative 1 times the quantity t minus 3 to the 5th, then f of t is negative t to the fifth, and that would go right here. And so now we've got e to the negative as times the Laplace transform of f of t. And then we just evaluate that. Well, the negative 1 can be pulled out as a constant, and the Laplace transform of t to the fifth can be found using this rule. The Laplace transform of t to the n is n factorial over s to the n plus 1. So we're going to have 5 factorial over s to the 5 plus 1, or s to the 6. And 5 factorial, I believe that's 120. I'm just going to use my calculator for that pretty quickly. Yep, 120. So we have negative 120 times e to the negative 3s over s to the 6th. So it's not too bad. You just have to do a little bit of pattern matching. Now, this is harder if you don't have something that looks like the input over here. If I have this as a function of t minus 3, if f of t minus 3 is a function of t minus 3, it's easy to replace the input here and the input here with a t and a t. This is not as easy because I don't have anything involving a pi over 4 on this one. But we're going to do the same thing, pattern matching. I've got a heaviside function, so I will be using the second translation theorem again. This is f of t minus a times h of t minus a. And since those are the same, a must be pi over 4. And that makes this f of t minus pi over 4. Well, then according to our theorem, we get e to the negative as, and a is pi over 4, times the Laplace transform of f of t. Now we've got to figure out what f of t is. I'm just going to leave some space, and I think this one is actually kind of long, so I'm going to leave it a lot of space this time. I'm not even going to put that second, what are those called? Braces, curly brackets, I'm not sure. Okay, so we've got f of t minus pi over 4 is equal to cosine of 3t, but I really need this to have a minus or t minus pi over 4 in it. So we're going to do what we always do. We're going to replace the t with t minus pi over 4, and that's legal. I'm just going to make it into what we want it to be. That's legal as long as we also compensate for that. So if I'm subtracting pi over 4 to get this to look like t minus pi over 4, that's fine as long as I also add pi over 4. And then if I distribute this 3 to that set of parentheses and that pi over 4, what we end up with is this. We've got cosine of 3 times the quantity, t minus pi over 4, plus 3 pi over 4. So I've got a t minus pi over 4 here now and a t minus pi over 4 here, and that gives me this result. This function is taking the input t minus pi over 4, and it's multiplying it by 3, it's adding this 3 pi over 4 to it, and then it's taking the cosine of the result. So for a general input, it's going to take that input, multiply it by 3, add 3 pi over 4, and then take the cosine of the result. So if my input is t, I end up with cosine of 3t plus 3 pi over 4. Now we don't have anything that looks like this in our table, but this is the function that we should be taking the Laplace transform of over here. If you're saying to yourself, how on earth do I take the Laplace transform of something that looks like that? Well, we can't take the Laplace transform of it in this form, but we can take the Laplace transform of it in an alternate form. So what we're going to use is this identity from trig. If you have the cosine of a sum, it turns out that that is the cosine of the first angle times the cosine of the second angle minus sine of the first angle times sine of the second angle. So using that, I can write this as a combination involving cosine of 3t and sine of 3t and cosine of 3 pi over 4 and sine of 3 pi over 4. Cosine and sine of 3 pi over 4 are just constants, so then I can use the linearity of the Laplace transformation to evaluate this expression here. So we'll have this. We have e to the negative as times Laplace transform of what? Well, it's going to be cosine of 3t, if this is my a and that's my b, times cosine of 3 pi over 4 minus sine of 3t times sine of 3 pi over 4. And you can get out your unit circle if you want to. I prefer to just draw a triangle over here in quadrant 2. If this is 3 pi over 4, this triangle is a 1 square root of 2 triangle because that reference angle is 45 degrees. The x distance is negative. Well, it's directed distance, right? Its directed distance is negative and the y is positive here. And so cosine of 3 pi over 4 is adjacent over hypotenuse. So cosine is negative over here. So this is negative 1 over square root of 2, which reduces or simplifies to negative square root of 2 over 2. And then over here, sine is positive, so this is positive square root of 2 over 2. Okay, and we actually have a rule for cosine of 3t and a rule for sine of 3t, so we can evaluate these guys. So we've got e to the negative pi over 4 times s times negative square root of 2 over 2 times cosine of 3t, the Laplace transform of that, plus square root of 2 over 2 times sine of 3t. Now from our table, or from the Laplace transforms that we have previously studied, we know that the Laplace transform of cosine of kt is s over s squared plus k squared, and the Laplace transform of sine of kt is k over s squared plus k squared. Well, for this one, k is 3, and for this one, k is 3. And we've got a linear combination of these guys, so it's just the Laplace transformation operator will apply term by term, and then we can factor out the constants. So we'll get negative square root of 2 over 2 times the Laplace transform of cosine of 3t. So it's going to be s over s squared plus k squared. Since k is 3, that's going to be a 9. And we'll have square root of 2 over 2 here. And then we're multiplying by the Laplace transform of sine of 3t, which is 3 over s squared plus 9. Now, if you want to, you could simplify this. We could call this e to the negative, oops, I don't know why I wrote pi over 2. That should be negative pi over 4 times s. E to the negative pi over 4 times s times a negative square root of 2 times s plus 3 square roots of 2, all divided by 2 times s squared plus 9. Now, that little bit of algebraic manipulation that we did is something that we often do when we are trying to compute Laplace transforms and inverse Laplace transforms in order to match patterns. But we can actually use that idea to come up with an alternate form of our second translation theorem. So let's say, actually, I'm not going to do another example here. Okay, so let's say we want to come up with an alternate form of the second translation theorem. Remember, the second translation theorem says that if f has a Laplace transformation, then the Laplace transformation of f of t minus a times h of t minus a is e to the negative as times the Laplace transform of s, and that works for s greater than a. Question is, well, how would that apply to g of t times h of t minus a? Well, in that case, if we're pattern matching, whatever g of t is, that's going to be f of t minus a, and this is h of t minus a. So we would still get this e to the negative as over here. The question becomes, if f of t minus a is actually g of t, what should I be putting over here in terms of this function g? Well, let's think about it. If I have f of t minus a here, and that's equal to g of t, again, I want this to be a g of t minus a, not a g of t. So in order to make this look like g of t minus a, I'm just going to replace the t with what I want it to be, and then compensate for that. And now, if I think of this as an input-output machine, the input is t minus a, and the output is g of t minus a plus a. So that would tell us that f of t in this case, or f of some input, is actually g of that input plus a. So if my input is t, that should be g of t plus a. Now remember, this is supposed to be the Laplace transform of f of t. So when we're coming up with this alternate form of the second translation theorem, we're just writing this in terms of this function g of t instead. Well, the Laplace transform of f of t in this case is the Laplace transform of g of t plus a. Basically, you're making a substitution, and then through a little bit of algebraic manipulation, you're able to show that if this is g of t, this needs to be g of t plus a. And I think that makes sense because this is f of t minus a, and this is the Laplace transform of f of t, which is what you get when you add a to this here. We're doing the same thing here. If I add a to this, I get g of t plus a. So here is my second version, or my alternate version of the second translation theorem. You probably will use this one actually more than you use this one. And both of these are in your table. So now let's do one more example. So let's say you've got t squared, and you are taking, and you're multiplying that by the Heaviside function at t minus 2. Well, according to that, if I'm matching patterns with this second, or this alternate version of the second translation theorem, a is clearly 2, because if this is h of t minus 2 and h of t minus 2 is h of t minus a must be 2. So we'll have e to the negative 2s. And then we'll multiply by the Laplace transform of g of t plus a. So we're taking g of t, which is t squared, and then we're replacing t with t plus 2. So that's going to be t plus 2 squared. Or if you write that twice in FOIL, you'll get t squared plus 4t plus 4. It's not t squared plus 4. You really have to write it twice in FOIL so that you get your inner term, or outer times outer and inner times inner is that 4t. Now you can also memorize that, but I highly recommend that you actually know where that middle term comes from. So we need the Laplace transform of g of t plus 2 over here, which is the Laplace transform of t squared plus 4t plus 4. And that can be computed pretty easily. The Laplace transform of t squared comes from applying this rule. We get n factorial over s to the n plus 1. So 2 factorial, which is 2, over s to the 2 plus 1, which is s cubed, plus 4 times the Laplace transform of t. So it's going to be 1 factorial, which is 1, over s to the 1 plus 1, or s squared. So we've got 4 times 1 over s squared, which is 4 over s squared. And the Laplace transform of 4, well, it's just 4 times the Laplace transform of 1, which was 1 over s. So we're going to have 4 over s there. Okay, so now we can use either the second translation theorem, which is written this way, or the second translation theorem, which is written this way. Now, sometimes this is convenient. Sometimes the function really is written in terms of t minus a, so it's very easy to see what f of t is. If it's less obvious, you can always do this. Okay, so we just took care of that one and that one. Now we are going to practice computing inverse Laplace transforms. I think we'll just do one example, maybe 2 examples. I think I will do 2 examples after all. So let's say somebody asks you to compute the inverse Laplace transform of e to the negative pi s over s squared plus 1. Well, in that case, as soon as you see that e to the negative as, you know the inverse transform is going to involve a heaviside function. Because here is our inverse transform version of this second translation theorem. The inverse transform of e to the negative as times f of s is f of t minus a, which is the same as taking the inverse transform of big F. That's going to give you f of t. You replace the t with t minus a, and then you multiply by the heaviside function at t minus a. There we go. Okay, so as soon as I see that e to the negative pi s, I know this is where I'm going. So I'm thinking of this way. E to the negative pi s times 1 over s squared plus 1. Just using pattern matching, this is my e to the negative as, and this is my f of s. Well, if e to the negative pi s is equal to e to the negative as, a must be equal to pi. And then if I want, and if this is f of s, I know how to find f of t. I just take the inverse transform of that. So according to this theorem, the inverse Laplace transform of something like this is the inverse transform of f of s. But then we're going to take our t and replace it with t minus a, which in this case is pi. And then we'll multiply by the heaviside function at t minus pi. Well, this is a k over s squared plus k squared, where k is equal to 1. So the inverse transform of that is actually sine of t. And if you're replacing the t with t minus pi, that's going to be sine of t minus pi times h of t minus pi. Now you can leave it like that for the purposes of our class, but sometimes you might check your answer somewhere and see that they have a slightly different version of that answer. And that's because when you take a sine function and you shift it by pi units to the right, it is a familiar function. So we know that the sine function looks like this. Question is, well, what if we started over here? What if we started at pi instead, so that it looked like this? Well, if I continue that pattern in both directions, well, we see that what we end up with is negative sine of t. So this is my sine of t minus pi, and then when I extend it, then I see that this pattern here is negative sine of t. So sine of t minus pi is negative sine of t. So you could also write this as negative sine of t times the Heaviside function at t minus, pi. There we go. And that would be the same thing because those are identical to each other. Okay, so that's how we do that. Let's do one more example. A lot of students get thrown for a loop whenever they see something that looks like this. But it is exactly the same thing as what we have been doing, or exactly the same thing as what we did in the last example. They look at this and they want to use partial fraction decomposition. They're saying, let's do partial fraction decomposition here, but they don't know what to do with the exponential in the numerator. You don't actually do anything with an exponential in the numerator. Partial fraction decomposition only works for a rational function. So you need a polynomial in S over a polynomial in S. And so you might think that, okay, well, if that's the case, then partial fractions doesn't work here at all. It doesn't work for the whole thing, but if you factor out that e to the negative as, you can think of this way. So this is your e to the negative as, and this is your f of s. So we're just going to use that theorem again. Here, a is equal to 2. And then we're going to need an f of t. We're going to replace the t's with t minus 2's, and then we're going to multiply by the Heaviside function. So that's the plan. I'm just going to write it down. And that's not an x, that's just multiplication of t minus 2, because we know a is 2. Okay, so that's the plan, but now we just have to do the partial fraction decomposition in order to find this. This expression here represents f of t. So we'll do that here. F of t is the inverse transform of f of s, and f of s is 1 over s squared times s minus 1. And we can rewrite that this way. This is a constant over s squared, or a constant over s plus a constant over s squared, because it's a linear factor that's repeated, plus a constant over s minus 1. And if I think of this as an equation, you're sort of thinking of this part as an equation, and I multiply by the LCD, well, yeah. This is what happens. The s's reduce here, or the s minus 1's reduce here. One of the s's will reduce here, both of them reduce here, and the s minus 1's reduce here. So we end up with 1 equals a times s minus 1 plus b times s minus 1 plus c times s squared. So we'll choose values of s that cause each of these factors to be 0. So an s equals 0, s is obviously equal to 0. So this term would be 0, and then this term would be 0. In that case, we'll have 1 equals b times negative 1. So b is equal to negative 1. And then if s is equal to 1, this is 0, and this is 0. So we have 1 equals c times 1 squared, which is obviously just 1. Okay, now we only had 2 factors. One of them was repeated, so we were only able to get b and c from this. We weren't able to get a from this. In order to get a, we need to substitute another value of s. I'll just pick s equals 2. So we'll have 1 equals 2 times a times 2 minus 1, which is 1, plus b times 2 minus 1, which is 1, plus c times 2 squared, which is 4. And I know that b is negative 1, and c is 1. So we end up with 1 equals 2a plus 3. And if we subtract 3 from both sides, we get negative 2 equals 2a. So a must be negative 1. Okay, so f of s is actually equal to this. It's a over s plus b, which happens to be negative 1 over s squared, plus c, which was 1, So I should circle those, over s minus 1. So I can take the inverse transform of that. And of course, that's a linear operator, so we just take the inverse transform term by term. The inverse transform of negative 1 over s is negative 1. The inverse transform of negative 1 over s squared is positive t. And this is 1 over s minus a with a equals 1. So this is e to the at, where a equals 1, so that's e to the t. Okay, so going back here, we have this. This is going to be negative 1 plus t plus e to the t. But then we have to replace the t with t minus 2 and multiply by the heaviside function at t minus 2. So we'll have negative 1 plus t minus 2 plus e to the negative, or e raised to the t minus 2 times the heaviside function at t minus 2. And then this can simplify. T minus 2 minus 1 is t minus 3. So I just want you to be aware, when you see a problem like this, where it looks like you should be using partial fraction decomposition, but you've got this exponential in the numerator, a lot of students are like, oh, I don't know what to do with the exponential. They try to do the partial fractions with the exponential there. Don't do that. Factor out the exponential, and then you're going to use partial fractions for the rational function that remains. Once you find f of t, or once you write this, rewrite this using partial fraction decomposition, then you can take the inverse transform like we did. Once you find f of t by computing that inverse Laplace transformation, then you will replace all the t's with t minus 2's, and you end up right here. Okay, so that is the end of our discussion of applications of the second translation theorem. I will see you in the next video where we work some initial value problems, or at least one initial value problem that features the first and second translation theorems, or just one of those. That would be fine, but I'll see you next time.